Memory has been a very constant part of computing architectures. Density increases and DRAM interfaces change and accelerate from DDR3 to DDR4 to DDR5, following a highly predictable path. But new processor architectures can no longer supply sufficient data by using this approach, and memory technologies are threatened with scaling limits, leading us into a time of great change. I'm Jim Handy of Objective Analysis.
And I'm Tom Coughlin of Coughlin Associates, and we're here to discuss the changes that are imminent to memory architectures, to provide some idea of what technologists must do if they want to keep ahead of the dynamic changes that are just around the corner. In this presentation, we will discuss why emerging memories, MRAM, phase change memory, resistive RAM, and ferroelectrics are already becoming necessary. Next, we'll talk about new ways to connect memory to processors, focusing on CXL. We'll explain how this finally brings disaggregation to computing's last holdout. Finally, we will talk about the new chiplet approach to packaging, and we will explain the UCIe interconnect standard. We'll also surprise you by showing that chiplets are actually an embodiment of Gordon Moore's law, as it was explained in his original paper back in 1965, and also a paper in 1970s. For now, let's chat about emerging memory technologies. There are four leading emerging memory types, all represented in this slide. MRAM harnesses magnetic properties to store bits within a semiconductor chip. A lot of valuable research continues to propel this technology forward. Resistive RAM comes in many different forms to provide an answer to the scaling limitations faced by established technologies. The most famous example of phase change memory, or PCM, is Intel's 3D crosspoint memory, also known as Optane. Despite Intel's winding down of the Optane business, the technology is still a good one, and it may rise to prominence at some future date. Finally, we have ferroelectric memories, or FRAM. This is the oldest emerging memory technology, having first been built in the 1950s. More FRAM chips have shipped than all other emerging memories combined. We're particularly fascinated by these technologies and have been publishing and updating a report for the past several years. This is the cover art for the most recent edition. We'll tell you how to obtain a copy at the end of the presentation. The Prism is a copy of the familiar memory hierarchy pyramid with four levels: cache memory, typically DRAM, SCM or storage class memory, and storage. All of the emerging memory technologies shown in the color spectrum are vying for a place in this hierarchy. So far, most of the emerging memories development focus has been on the technologies and their attributes. 3D crosspoint or Optane brought a new focus to the economics of emerging memories. Now let's see about that. We believe that the spectrum of emerging memories will become more fiscally focused. To that end, we bring you the Eye of Provenance, an image on the back of the US $1 bill. Once again, we divide the hierarchy pyramid into cache, memory, storage class memory, and storage. And once again, we show a spectrum of emerging memory technologies. But this time, they're looking near and far for applications in which they make economic sense. But this pyramid is in a circle. Let's look at a different but highly relevant circle. I'll bet you didn't expect to see a pie chart. This is a look at today's memory market, which totals $133 billion last year. DRAM accounted for the largest share at 61%, and NAND took most of the rest at 36%. All of their memories combined account for only 3% of the market. NOR, SRAM, EEPROM, MRAM, EEPROM, MRAM, PCM, FRAM, and various specialty memories. Clearly, any memory that wants to make it big will need to displace either DRAM or NAND flash. How will they do this? This chart shows how emerging memory companies have been hoping things will develop. On the horizontal axis, we have processes in backwards order, running from large on the left to small on the right. This roughly follows the timing of these process nodes. On the vertical axis, we have a log scale of memory prices. When we build a chart this way, then Moore's law becomes a straight line, with relative price per megabyte falling in proportion to the process geometry. Both lines follow this price decline, with the upper black line somewhat higher than the lower red line, which represents the higher cost of processing an emerging memory technology's wafer on the black line compared to standard silicon in the red line. Today's technologies are expected to hit a scaling limit soon, where bit cells will no longer be able to shrink in proportion to process technologies. This is called a scaling limit. When that happens, any emerging technology that does not have the same scaling limit should be able to reach a lower cost within the next 1 or 2 process generations than the established technology. The emerging technologies market will then be taken over by the cheaper emerging memory. NAND already hit its scaling limit at 15 nanometers, but designers cleverly figured out how to move into the third dimension to provide it with a considerably longer future. Another technology embedded in NOR flash in microcontrollers and ASICs reached its scaling limit at 28 nanometers. Embedded SRAM is also starting to run into trouble, opening a new potential market for emerging memories as cache memories and scratch pads. Not only will they be cheaper than their SRAM counterparts, but they consume less die area, and they will also be persistent, and that opens the way to new system architectures. But embedded memories are slow to change, and it will take some time before embedded emerging memories become prevalent. But this will happen in time. Our report provides a detailed forecast of how that will happen. That means that embedded emerging memories are inevitable, and that NAND should not be expected to yield to an emerging memory technology anytime soon. That leaves DRAM, the biggest memory market, as the target. Intel's Optane technology went up against DRAM in a relatively oblique way and incurred over $7 billion in losses by our estimate. It's clearly too early for an emerging memory technology to cannibalize the DRAM market. Over time, though, we expect for this to change, but again, it will not happen soon. Still, important changes are happening in emerging memories, and we recommend for audience members to maintain an awareness of them, since they will eventually become mainstream, and that will drive changes in software and computing architecture. And Jim's going to tell you about those.
Let's switch gears and discuss a hot new system architecture called Compute Express Link, or CXL. CXL has been embraced by 2 communities for 2 completely different reasons. Hyperscale computing companies like CXL because it allows them to disaggregate memory, the same way that they disaggregated computing resources and storage. Memory has been the last holdout for this trend. Hyperscalers like the fact that they no longer will have a lot of stranded memory in their data centers, which is wasteful, since the stranded memory is costly and it consumes a big chunk of the data center's energy and cooling budget. I'll explain what stranded memory is in the next slide, and then you'll understand. At the complete opposite end of the spectrum, memory manufacturers like CXL because it supports memory pools, a resource into which they hope to sell a lot of memory chips to boost their sales. It's a little confusing to observe that hyperscalers want CXL because it will reduce their DRAM purchases, yet DRAM manufacturers like CXL because they believe that it will motivate hyperscalers to purchase more memory. This is part of something that I call the CXL conundrum. But let's get back to stranded memory. What does that mean? Let me show you with a little animation. This is a sketch of a simple virtualized system made up of 4 servers. Each server has a certain amount of memory. For the sake of simplicity, we'll say that this system only runs 2 application programs. The memory size of the servers is determined by the amount of memory used by the application that needs the largest memory. So here's a representation of memory use in these systems with a smaller memory application. The blue represents the memory that the application uses, and the gray represents the memory that is not needed. The big memory application moves from server to server in this virtualized system, so each server must contain enough memory to run this program efficiently. In this system, there are always 3 servers that have more memory than they need, although you never know which server that is. This memory is the stranded memory in the system. So what do you do about this? With CXL's shared memory system, you can reduce the size of each server's memory to fit smaller memory applications. Then you add a memory pool to the system. This memory is not assigned to any processor. When the large memory application causes one of the servers to need this resource, then it gets assigned to that server. As the application moves from server to server, the memory is allocated to the server that currently needs it. Since the memory is now efficiently used by the system, CXL eliminates the stranded memory in the system. The system becomes more efficient user of memory, reducing the capital cost and the power cooling costs at the same time. But let's look at other benefits that CXL will bring to the system. CXL supports memory of different types. This will be a benefit to emerging memories. By supporting a variety of memory speeds, CXL supports the use of multiple memory types on a single memory channel, something that DDR simply could not do. CXL advocates the term NUMA, or non-uniform memory architecture, for this support of different speeds. In a similar vein, CXL supports memories whose writes are slower than its reads, which is common among emerging memories. Let's now move on to chiplets, a new approach to continuing Moore's law that takes advantage of CXL's protocol. CXL has been defined to support persistence. This was instigated to support Intel's Optane memory, but it's a feature that is generally useful for emerging memories since all emerging memories are persistent. But you don't need an emerging memory to use CXL. A new SSD architecture known as memory semantic SSDs use the CXL interface to provide persistent memory functions to computer systems before emerging memories become mainstream. These SSDs, which team very fast NAND with a large internal DRAM, allow applications to access the SSD's data through memory load store semantics, using the SNIA NVM programming model. Tom will now explain another new change that is already well underway.
Chiplets are cool. This approach, which has only recently entered the mainstream, is really taking off. You will understand why in a minute. But this is not what chiplets are about. We recommend not putting these chiplets into your mouth and chewing on them. Chiplets are about continuing along Moore's law. This graph is from a 1975 paper that Gordon Moore wrote in review of his 1965 paper that was the genesis of Moore's law. In this chart, he attributes the growing number of components on a chip to three phenomena. The bottom line is the contribution from the growing size of the die, or the chip's area. The next higher line is a contribution of dimension reduction, which most must refer to as scaling, or the lithography scaling. Scaling is a migration from one process technology to another, to shrink the size of the transistors on the chip. A lot of people think this is all there is to Moore's law. The next higher line combines two lower lines to show the transistor count based on these two phenomena alone. These are the two that are easy to measure, die size and process, but they didn't account for what was actually happening in the industry. Chips were getting increasingly complex at a faster rate than these two factors could account for. As he showed in the top line, Moore attributed this to cleverness, small tricks that designers create to get more out of the increases provided by the bottom two lines. These days, a lot of people call this cleverness more than Moore, but Moore actually flagged this phenomena back in 1975. But today's problem is that the lowest line on this chart has reached an endpoint. Die sizes have become limited by the optical lithography tools and are not expanding past the maximum reticle size to slow the pace of development. Meanwhile, processor complexity continues to advance. CPU architectures are ready, willing, and able to continue adding cores and caches to their processors. How do we deal with this? The answer is to add chiplets to virtually increase the die size. This approach opens doors to all kinds of possibilities. One in current use is the high bandwidth memory, HBM. This is a stack of DRAM chips that is in close contact with the processor to provide the highest bandwidth at the lowest possible latency. But other functions in memory can be added as chiplets. AMD has used chiplets very successfully to drive the processor I/O pins. Emerging memories are likely to find their way into processor packages as chiplets, since they can offer higher speeds, lower cost, and persistence, but use processes that differ from the performance CMOS logic processes that are preferred for CPUs. Look for MRAM and resistive RAM chiplets to find their way into processor packages as chiplets within the next 5 years. I should note that Gordon Moore also predicted the use of chiplets in his original 1965 paper. His clairvoyance in insights is simply amazing. This is a photo of an NVIDIA GPU that uses chiplets. We're just showing it to give an idea of the kind of system that is starting to enter the mainstream. These chiplets all need to communicate, and Jim's going to tell you about how that's being managed.
How will chiplets communicate with one another? Today, HBM uses a JEDEC standard interface, but other chiplets communicate using proprietary interfaces. Chips from Intel, AMD, and even Global Unit Chip all employ proprietary signaling to communicate within a module. This drives costs up, especially when different chiplets are designed to provide the same features, but each with a different chip-to-chip interface. If one standardized design could be used, possibly sourced by a third party, then its higher unit volumes would help to reduce the cost, and this would be to everyone's advantage. Enter UCIe. The Uniform Chiplet Interface is fundamentally a CXL interface for chiplets. This springboards off of all of the valuable work that has been done to define CXL to create an equally useful interface between chiplets. As we mentioned before, chiplets can help to combine a processor based on performance CMOS logic with a memory using an emerging memory technology that is built using a different process. This should benefit both chips that use embedded non-volatile memories as well as processors. The following slides will explain how a processor can benefit from using chiplets for its cache. Embedded NOR can't shrink past 28 nanometers. Embedded SRAM eases off its scaling at about the same process, yet it doesn't reach a hard stop. It simply doesn't scale with process. Yet emerging memories have plenty of room to scale, with some even improving in performance the smaller they shrink. Let's look at embedded SRAM as a technology that could easily yield to an embedded emerging memory, even today. The chip at the right is an Intel microprocessor. You will note that slightly more than half the area consists of its SRAM. Part of the reason that this SRAM caches on the chip is because it's so fast compared to DRAM. But an emerging memory is also faster than a DRAM, and even though it may not be quite as fast as an on-chip SRAM cache, it can be significantly larger than the SRAM at an equivalent cost. And cache design involves trading off size against speed. The slower, larger option is quite likely the path to higher performance. Since the chip is made on a high-performance CMOS logic process, its cost will be pretty high. Add to this the fact that each bit uses 6 transistors as opposed to the 1 or 2 required by an emerging memory technology, and it's easy to see that a separate emerging chiplet might cost far less than this SRAM that contributes over 50% of the cost of the processor. SRAM doesn't scale with process anymore either. This slide illustrates that fact. Here again, we have an Intel processor with its logic and SRAM portions. Until recently, scaling the chip to smaller process nodes makes the die size scale with the process geometry. This is shown by the red line. But what happens with today's processes? Keeping the logic and SRAM processes in mind, we scale the two parts of the chip separately according to the figures from recent research papers. The SRAM doesn't scale in proportion to the logic. In fact, the die area almost levels off due to the large size of the SRAM, while the logic continues to shrink. The memory is dictating the size and the cost of the chip. Costs would clearly benefit from the separation of these two portions of the processor. Chiplets, and particularly emerging memory chiplets, would seem to be the best way to go here. So where does this lead us? First, we see that emerging memories are necessary and that they are right around the corner. With their persistence, we automatically will gain access to persistent caches, which could open up a whole new world of processing. Second, expect for CXL to become the new standard in computing architecture. With CXL come new ways to use memories, both in pools and in the use of persistence. Finally, we expect to see widespread use of chiplets in the near future, and with that, we should see widespread adoption of an emerging memory technology. All of this is spelled out in our emerging memory report. It's available for sale on both of our websites at the URLs shown here. Please have a look if you'd like to know more. And now we'll open up the floor to questions.